Okay, there we go. We're recording. Okay, so let's talk about artificial intelligence. Um, so just a couple of background notes on artificial intelligence. So in reality, artificial intelligence, from a computer science perspective, doesn't actually have that much to do with profound questions about the nature of intelligence or the nature of human identity. So for those of you who took the science fiction freshman preceptorial, it's a little bit misleading. We're not actually going to think about, whether clones are human and whether the artificial intelligence in the androids from Blade Runner are human. That's not really what we're all about. In reality, we're going to do a lot of graph traversals or possibly lots of statistics. And you've already seen some a flavoring of the statistical side of artificial intelligence when we talked about the Bayesian spam filter. That's actually the classification problem of classifying a bunch of documents or a bunch of pictures or a bunch of something into two separate categories or possibly more categories using Bayesian inference. It's actually a classic artificial intelligence problem. And so now we're actually looking at another type of classic artificial intelligence problem. We're going to do graph searches. This is still totally awesome, but once again, it is different than kind of the popular understanding of artificial intelligence where you've got like robots and 3 laws of robotics and whatever else. So extremely broad outline. There's one-player games, sometimes known as puzzles, and then there's two-player games. So one-player games, 8 puzzle, which we'll see an example of, pegboard, free cellar, solitaire, Rubik's Cube could go on here, other things. There's also two-player games, chess, checkers, Settlers of Catan, Risk, things like that. Settlers of Catan and Risk, you can actually play with more than 2 players, but the rules for how you would do a 2-player game actually generalize to 3 or more players. So we're just going to lump all that in with 2-player games. And of course, for this lecture, we're focused on 1-player games. Next lecture, we'll actually focus on 2-player games. So 1-player games are sometimes called puzzles. At least I call them puzzles to differentiate them from 2-player games, which are kind of more like true games. Now, I say sometimes they're known as puzzles because I call them puzzles, so clearly somebody does it, so sometimes it happens. I actually don't know if this is a general term in artificial intelligence, but it's one that I'm going to use. So 1-player games, I'm going to call them puzzles. So here's sort of an outline of what we're going to talk about with 1-player games. We'll start with an example, the 8 puzzle. We're actually going to use this as our motivating example. I have no idea what this bullet point was supposed to be playing this, I'm not sure. We're going to see an example of it. We'll talk about graph representations, known and what I'm calling semi-known goals, a way of formally defining the problem, and then solving it with the artificial intelligence and modern approach framework, and then improving on just sort of a straight depth first search using a heuristic type of search. So 8 puzzle, this is a classic sliding block puzzle game. I'll show you. The heck did it go? Oh, that's not it. Here we go. So here's our example. So we've got these 8 blocks, and we can slide these tiles around, and we want to get it into some specific format. Like usually it's sort of 1, 2, 3, 4, 5, 6, 7, 8 with the blank in the middle. Sometimes it's like 1, 2, 3, 4, 5, 6, 7, 8 with the blank at the end. But there's some goal state, and we're going to move these puzzle pieces around in this 8 puzzle, trying to find, and they call it the 8 puzzle because there's 8 numbers and then there's the 1 blank. I guess if it were, this puzzle predates computer science, but if it were specifically a computer science thing, it might be called the 7 puzzle because the numbers would be 0 through 7. But as it is, it's known as the 8 puzzle. So you can think of searching through the state space of the 8 puzzle as a graph. So you start up here with your initial state, which is just sort of your mixed up version, and suppose this is our initial state. Well, there's 3 possible moves from here. We can move the blank up, left, or right. I mean, I realize that's also sort of like moving the 6 down and the 7 right and the 5 left, but since the blank is always the one that's going to get a new tile, you can actually just think of it as like moving the blank or swapping the blank. So if we move the blank left, we end up here, up, we end up here, right, we end up here, and then from here with the blank in the middle, there's 4 possible moves, so we can go ahead and sort of move the blank around there, and then we could expand this node. We could also expand some of these other nodes as well. And so that's our general way of thinking about 8 puzzle as kind of a graph search problem. And of course, down here you can see this is the goal state that we're looking for. This particular way of defining the goal is you kind of want all the numbers in order going around the edge. And so, you can sort of see there is a path through this tree to get there. Now, an interesting question, well, how similar is 8 puzzle to other puzzles? I mean, this doesn't look like solitaire. It doesn't look like a Rubik's Cube. Is this actually similar? And the answer is they're actually very similar. So similar, in fact, that we can actually use the same process to search for the goal state for any one-player puzzle. We can sort of write the code once and then plug it in and just solve it for any puzzle. So to solve a puzzle problem, broadly speaking, what you're going to do is you're going to set a root, which is the initial state of the board. That's the root of your tree. Every move is an edge to the board state resulting from that move, and we're basically going to perform depth-first search until we find the goal state. And so that's like just a really, really simple way to think about solving a puzzle. I want to mention there's 2 kinds of goal states. They're not really separate. They're really just goal states, but there's kind of 2 ways to think about it. There's a known goal state, so we know exactly what the goal state looks like. Like, for example, with 8 puzzle, we know we want the tiles in a certain order, and we know what that order is and exactly what it looks like, but we don't know the sequence of moves we would need to make to get to that goal state. So we'll call that a known goal state. An unknown or semi-unknown goal state, this is something where we can quickly verify if a state is a goal state, but we don't actually know exactly what the goal state's going to look like. So if you give me a state, I can tell you if it's right or not, but I don't actually know what the goal state looks like. And usually with this sort of problem, we don't really care about the sequence of moves to find the goal state. We just want to know what the goal state looks like. And so I'll give you a couple of examples. Known goal state, obviously 8 puzzle. The pieces are supposed to be in a certain order, and what we really want is a sequence of moves to get the board to this goal state. That's how you would solve that puzzle. Rubik's Cube's another possibility. The goal state, you want the same color on all sides of the Rubik's Cube, and we want to know the sequence of turns and twists to actually get the cube, that should say cube, into this goal state. So an unknown or semi-unknown goal state, this would be something like n queens. N queens is a classic artificial intelligence problem. You have an n by n chessboard and n queens. You want to place those n queens on the board such that none of the queens can attack each other. Now, if you give me a board, an n by n board with n queens on it, I can very quickly tell you if this is a goal state. In other words, I can very quickly look at the board and tell you if any queen can attack any other queen. And I don't really care what the sequence of moves is. I don't really care what order you put the queens on the board. What I care is, what does this board look like? So I can quickly verify that this is a goal state, but I don't know precisely what the goal state looks like, because if I knew what the goal state looks like, I wouldn't actually need to solve the puzzle. So this is a little bit different than 8 puzzle or Rubik's Cube or Solitaire or something like that, where I know exactly what the goal state looks like, I just don't know how to get there. Here's a situation where I don't know what the goal state looks like, though I can quickly verify if a configuration is a goal state, but I don't really care what order I'm going to lay the pieces out. So just sort of here's a picture. This is a n queens, where n is 8. So we've got 8 queens on an 8 by 8 board, and none of these queens can attack each other. Remember, queens can attack across the rows, across the columns, or diagonally. And actually, these 8 queens are laid out such that no 2 queens could actually capture each other. And for any n greater than, can you do it for 3? I don't think you can do it for 3. Nope, can't do it for 3. For any n greater than 3, there is a solution to n queens, it turns out. But finding it, especially for larger boards, is very challenging. So we want to be able to formalize a system to solve any puzzle problem. We want to kind of come up with a standard way of thinking about puzzle problems. And I should note that this does assume infinite time and possibly infinite space, because depending on what traversal algorithm we use, and how deep the goal space is, we could still be dealing with exponential solutions. So it may not actually run in a feasible amount of time, but assuming infinite time and space, we can actually come up with a way of formally solving any of these puzzles. Now, there's fairly standard terminology and a fairly standard formalization that comes out of Russell and Norvig's Artificial Intelligence: A Modern Approach, this AIMA or AIMA. This is the textbook used for the AI course at Knox. This is a very formal way of defining it. It comes out of a world where you're programming typically in Lisp, which is not object-oriented, or at least not normally object-oriented. And so you're working in a world with lots of functions. So when we define this formally, we're going to be talking about functions. But then when we talk about implementing it in Java, we're actually going to talk about doing it with object-oriented programming, which is going to mean that we still sort of have functions. We're going to implement them with functors, which are like little interfaces with one method. But for the most part, all of the interesting stuff is going to be encapsulated using object-oriented programming. So the formalization of puzzle problems, we need to have an action function, a results function, a goal test function, and a state cost function. And so I'm going to go through each of these. So an action function, this is a function that you apply it to a state, and you get back some list of actions, A1 to AN, and those are possible actions you can take from that state. So big picture here, given a state, you apply the action function, it gives you a list of all the legal moves you could make from that state. So you saw this with 8Puzzle. You can move the blank in certain directions, but if it's in the middle, you can move it in 4 places. If it's in the corner, you can only move it 2. So the action function, given a state, it'll tell you what are the possible things I could do, what are the possible legal moves I can make from this state. The results function, this is a function f given a state and an action that returns a new state s prime. So basically, this just means, okay, I'm a function that takes a state and an action and returns the new board state that would result, or the new puzzle state that would result from applying that action. So looks very formal, but kind of easy, intuitive notion of what's happening. There's the goal test function. This is great. F of s, given a state, let me know true or false, is this a goal state? This is pretty simple. And then finally, a state cost function. Given a state s, give me back the cost of that state. This is useful if actions might bring us to states that have different costs. Maybe you've got some sort of a puzzle where you're trying to certain board states are more expensive than others, and so you want to try to avoid those. In practice, we're going to deal with puzzles that all have a uniform cost. The cost of everything is essentially going to be 1. And so when we talk about finding the optimal or minimal solution, we're really just talking about the shortest path to the solution. We're not really worried about cost. But it is possible to have cost, and this is very useful for problems where you actually would need this. So, in summary, action function gives us a list of legal moves for a state. Results function applies a move to a state to produce a new state. The goal test function is this state a goal. And the state cost function, we're not really going to use this for our lab, and we're not really going to use this at all, but it is good to know that it is possible to add a state cost function if you have states that are more expensive than others. So to implement this in Java, we're not going to write functions because Java is object-oriented. We're actually going to do most of our coding in an object-oriented way, but we're going to write these little classes that implement special interfaces. And there's actually a big Java framework. There's also one in Python, and I think there's one in Lisp as well, that comes with this textbook. It doesn't come with the textbook. You download it from GitHub somewhere. But it's got some frameworks in multiple different languages where if you implement your code a certain way, it will actually solve your puzzle for you, which is actually really kind of cool. And it really re-emphasizes this point that all these puzzles are basically the same. They all look really different, but fundamentally, they have a state. You come up with some sequence of legal moves from that state, and all of those moves will bring you to some new state, which you can then kind of repeat that, and either you're at the goal state or you're not. And given just basically those 3 functions, because we're not worrying about the state cost, you can actually solve any puzzle. You can build a framework that will solve any puzzle. So this is a little bit of the pre-lab. You know what? I've just suddenly decided I'm going to skip through the pre-lab stuff and put it into a separate lecture. So boop-a-da-boo, 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 boop-a-da-boo. Great. Okay. That's going to go into a separate pre-lab lecture. So the question is, can we do better than depth-first search? We could do a depth-first search. We like depth-first search because it's actually quadratic in space, even though it's in worst case exponential in time. Of course we can do better than depth-first search, or we might be able to do better than depth-first search. Otherwise, this really wouldn't be very fun. Depth-first search is an uninformed search algorithm. It's just sort of blindly cruising along. We'd like to come up with an informed search algorithm that's going to try to explore the most promising-looking subtrees first. So here's the idea. This heuristic we're going to use is called A star. There's some etymology that goes back to the 60s as to why this is called A star when a lot of foundational AI work was being done. Apparently there were other A algorithms, and this was known as A star because it incorporated all of them or something like that. But the key understanding of A star to start with is it's a search algorithm, but it's going to use a heuristic that's going to try to guess how close a state is from the goal state. Now, the heuristics, these are just guesses. They're frequently going to be wrong. They're probably almost always going to be wrong. But what we're hoping is that using these heuristics is better than not having any heuristic at all. So we can come up with some possible heuristics for 8 puzzle. So the question, if on the left, if this is what we want, this is our goal state for 8 puzzle, how far is the state on the right from the goal state on the left? We want to come up with some number. So an estimate of like how many moves would we have to make here to get here. Now, if we knew the exact number of moves and we knew what they were, we'd be done. We would just go ahead and apply them. So we want to come up with some kind of a guess. So here's 2 possible heuristics. One, we could just count the number of tiles in the wrong place. So, only 2's in the right place. Everything else is in the wrong place, so including the blank. So let's say 8. There's 8 tiles that are all in the wrong place. Or we could maybe say 7 and just sort of ignore the blank, because if all the numbers are in the right place, then the blank has to be in the right place. So I mean, that's one possible heuristic. Another possible heuristic we could use is Manhattan distance. So we could say how far are tiles from their proper places, and we have to count the diagonals as 2. And so the idea with well, I think Manhattan distance is on the next slide. I should note these are 2 possible heuristics. There's many other heuristics. There's actually branches of artificial intelligence that study heuristics and ways of coming up with heuristics, and there's a lot of heuristics for a lot of different types of problems that lend themselves to A star. I'm not going to go into these in too much detail. I do want to elaborate a little bit on Manhattan distance. It's a really cool idea, in case you haven't heard of it. So we're going to go through each of the 8 numbers, and we're going to figure out how far is it from where it's supposed to be. So 1 is 2 spots away, so 1 would have to move here and move here. 2 is obviously in the right place, so that's 0. 3 would need to move 3 spots away. We would want the 3 to be here, so it would have to go 1, 2, 3. And the way the Manhattan distance comes in, if 3 moves up 1, you can see it's sort of diagonally away from the space it's supposed to be. But if you think about the way streets work in Manhattan, if you need to get from this corner over here to this corner, you can't just go directly. You have to go up a street and then turn right and then sort of go over a street. And that's how you would get to blocks that are catty corner away. And so this notion is called Manhattan distance, and it shows up a lot in artificial intelligence and in other parts of computer science. So similarly, 4 is 1 spot away. The 4 is supposed to be here. 5 is 2 spots away. 5 is here. We'd have to go 1, 2. 6 is only 1 spot away. Would have to go up 1. 7 is, of course, 4 spots away. Would have to go 1, 2, 3, 4, or possibly 1, 2, 3, 4. But either way, it's 4 spots away. And then 8 is 2 spots away. We'd need to go 1, 2. So add all that up, we end up with, I think, 15. So the Manhattan distance heuristic would be 15. If we were to just move stuff around willy-nilly, it would take at least 15 moves. Now, I should note that these heuristics, they're all underestimating. you can't actually just sort of drive puzzle pieces around. You have to do everything based on moving things in and out of that blank spot and basically moving the blank all around. Um, but we hope that our heuristics are sort of giving us kind of like a bound. So it's like, well, even in the best possible situation, you'd have to move 15 pieces around from that particular state to get to the solution. Good heuristics are hard to come up with. There's entire branches of research devoted to this. But what we're hoping is using these heuristics to give us some rough estimate as to how close a particular state is to the goal. It actually means we're more likely to expand promising nodes before we expand unpromising nodes. So if you've got one state, if you have a choice between two possible states to expand next, and one of them has, 3 pieces in the right spot, and one of them has only 1 in the right spot, well, the one with 3 in the right spot, that's closer to correct, so maybe we should try that one first. We're not guaranteed that that's going to be any better, but we're hoping it's going to be a little bit better, so that's what we're going to try. Now, I should note, we call a heuristic admissible if it underestimates the number of steps to the goal, to the solution. AI has a lot of terms that don't really make sense. I don't really know what the etymology behind calling it admissible is. But that's what it means. A heuristic is admissible if it always underestimates the true number of moves to the solution. And so you can see for 8 puzzle, going back a couple of slides, Manhattan distance and number of tiles out of order, these are both clearly underestimates. Going by the number of tiles out of order would come up with either 8 or 7. You really can't solve this in 7 or 8 moves. There's going to be more moves required than that. But that would be 7 if, in the best possible situation, we could just like pick up tiles and switch them around, which obviously you can't. So we're never really going to overestimate with either of these heuristics. F of n, this is the function. This is going to be our estimate of how close we are to the goal, state from a particular state n. So the f of n, this is g of n plus h of n. Now g of n is the cost from the root to n. We actually already know this because if we're looking at node n, that means we have some path to node n. It's one of the nodes we're considering expanding its subtree next. And then h of n is the estimate, in other words, our heuristic guess, of the cost from n to the goal. So f of n, this is our estimate of the total number of moves to the solution. And we're always going to expand the one that is shortest first because we're looking for an optimal solution. Optimal solution means the one that's closest to the root. You can imagine there might be multiple ways to get to the solution. There certainly are in 8 puzzle because you're allowed to have cycles. You can sort of move pieces all around and get back to states you've seen before. So there could be non-optimal ways to get to the goal, but we always are searching for the optimal way to the goal. So for example, what is f of n of this node? So, here's the root, here's this node, and its estimate is 3. Think about that for a second. What's your guess? Did you say 4? If so, you're right. We know that g of n to here is 1, and then the estimate to the goal from here is 3. So so f of n, the total guess of total number of moves from the root to the solution through this node, the guess is 4. Now, it may not actually be 4. It may actually be a lot more, but that's what the guess is coming up with using our heuristic. Similarly, what's f of n of this node? I'll give you a second to think about it. This one would be 2. We know, well, wait, no, that's not true at all. It would be 3. Because we know the true cost to this node is actually 2, and then the estimate from this node to the goal is actually 1. Now, it may not be 1. It may actually be a lot more, but what this heuristic is saying, 1, it's saying, well, this node looks a lot more promising than these other nodes, although this is sort of way down, one layer below these other nodes. So that's the sort of a very brief overview of A-star and heuristics. I should note that A-star is often used for trying to find paths or routes to navigate somewhere, possibly over a graph or possibly over terrain or something like that. And we'll do some in-class activities We'll do some clicker questions about all of this, but we'll also do some in-class activities about a lot of this as well, trying to go ahead and apply A-star. Awesome.